What's up, amigos? Today we have the aerodynamics of turning vanes. So this is a particular type of situation where there aren't any actual walls confining the turning vanes. So typically turning vanes you find in wind tunnels, and they're used to turn the flow, particularly around corners, 90-degree corners. But the thing with these turning vanes are that they are usually boxed in by four walls, which means that the flow has to get channeled through the turning vanes. Now, this is not necessarily a problem in this type of application because it works very well. But what happens when you put turning vanes out in the open where the flow doesn't actually have to be channeled through a particular area? In other words, would the pressure differences that you find going through the turning vanes affect the flow? Would it make the turning vanes still perform decently, or would it be not very good? So that's what we're looking at here. So first of all, we have turning vanes, and we have a bunch of them stacked up, you can see. And we have two Y planes, and they're colored in the velocity magnitude, and they're clipped so that anything below 0.95 meters per second, which is pretty much the entire wake, is visible. So this is the wake here. And we can see that the wake is not very streamlined. So first of all, the flow is not really turning very well. Secondly, the flow is not staying steady, so there is a massive wake. Now, why is that? We're going to look at some other cuts, some other views that will show us more, but it's probably because the flow has somewhere else to go. So let's move on to those views now. So now we have two Z-planes. We're looking a little bit up from underneath at the turning vanes, and the flow is from left to right. And the reason why we have two planes here is I put one right through the middle of these turning vanes so we can see what the flow is doing there. But I also put one just above the turning vanes, which technically the flow is not, well, in a confined space, there is no such thing as a flow here. But because this is an open space, the flow can be redirected around the turning vanes and actually go through the turning vanes. And this is what we're seeing right here, because if the flow was going through the turning vanes, there would not be this wake, this blue velocity, this like blue coloring, which is a low velocity, above the turning vanes. It should still be red 1 meter per second, but it's not. So this shows that some of the flow is moving away from the turning vanes. It's not going through the turning vanes. So why is that? The main reason is because if you think about turning vanes, they are doing work on the flow. So they're or more accurately, they're turning the flow, so it's creating a pressure difference. So there's more pressure inside the gaps between the turning vanes than elsewhere in the flow. So that means that the flow is going to go to the low pressure regions instead of the high pressure regions, which results in it being deflected away from the turning vanes effectively. And we can also see around the turning vanes, so if you look at the plane that goes straight through the turning vanes, that there is a lot of flow that does still move around, and the flow going through is not turning very well. It's very chaotic, which means that potentially the flow is also separating to some extent. And that may be due to the fact that, again, the flow going through is not going to be that fast moving because there's going to be some deceleration due to the back pressure. And again, in a confined space, this is not the case, but in an open space, it is the case. And now we have a few X-planes going downstream. So one just downstream of the trailing edges of the turning vanes, and then another two more downstream. And this shows us the extent of the wake. So again, this is clipped so we can only see the wake. And you see that around the turning vanes, like if you look at just how far the wake extends, it's pretty much making the entire surface area of the wake, the cross-sectional area of the wake, about twice as much as what the turning vanes are. So it's significantly greater than the turning vanes themselves. What's more, the turning vanes in practice should not have a wake, or at least a very small wake, because the flow should stay attached completely, and there should be minimal like velocity deficit. But obviously that's not the case here because it's not being put in an optimal situation. What's more, downstream we can see that there is this unsteadiness in the wake, and it's very close to the turning vanes, which means that the turning vanes themselves are probably not even having attached flow, which I guess we saw in the Z-plane views. And this is creating like vorticity and all this junk that's just breaking down very quickly. So that's the end of the simulation. I hope you find it interesting because I found this really interesting, seeing how turning vanes work in an environment that they're not designed for. And it shows that the environment that they're designed for really makes or breaks them, as it does with a lot of other aerodynamic situations, other aerodynamic flow control devices. So make sure to like, subscribe this. And if you want to get better at CFD or theory, check out our courses in the link in the description. And I'll see you in the next simulation. Peace out, amigos.